Tonight, we're retaking you on a journey into one of the most mysterious and fascinating questions humanity has ever asked. What are space and time, really? From the ticking of a clock on your nightstand to the distant glow of galaxies millions of light years away, we'll explore how scientists have redefined our understanding of these two invisible pillars of reality. You'll hear about the genius of Albert Einstein, the mind-bending theories of modern physics, and the way these concepts shape not just the cosmos, but the way you live your everyday life. Before we begin, if you enjoy drifting into these deep, thought-provoking explorations, please take a moment to like this video and subscribe to Science for Sleep. It's the best way to keep your curiosity alive and your nights filled with wonder. I'd also love to know where you are in the world right now and what time it is for you as you re-listening. Is it the middle of the night? A quiet afternoon? Let me know in the comments below, and when we're done, share your thoughts on how this journey into space and time made you feel. Now, settle in. Close your eyes. Let's dissolve the edges of your everyday world and step into the boundless mystery of space and time. Imagine holding an empty coffee cup in your hands. You can feel its weight, its smooth surface, the faint warmth if it's been freshly rinsed in hot water. You know that inside, there's nothing, just air. But is it really empty? That nothing is actually space, and even though it looks like a void, it's far from meaningless. Space is the stage where everything plays out. 'Tis the arena in which planets orbit stars, in which galaxies form, in which your coffee cup exists at all. And then there's time, the invisible current that carries all events forward. Without time, there's no change, no sunrise, no heartbeat, no stories to tell. For centuries, we thought we understood these two things. Space was simply the emptiness that held stuff. Time was the steady tick of a universal clock. They were separate, absolute, and fixed. Then came a quiet, deep-thinking man named Albert Einstein, who dared to suggest that space and time are actually one thing, a single fabric, woven together, bending and stretching, flowing differently depending on where you are and how fast you're moving. Before Einstein, Isaac Newton's ideas ruled. Newton imagined space as an unchanging, eternal container, like a perfectly smooth, infinite chessboard on which the pieces of the universe moved. Time, to Newton, was universal, ticking the same for everyone, everywhere, no matter what was happening. This made intuitive sense, because in our daily lives, it feels true. If you and I synchronize our watches and go for separate walks, we expect them to still match when we meet again. That's the everyday illusion of time. But under extreme conditions, near the speed of light, or close to a massive object, this intuition breaks down entirely. Einstein's theory of relativity shattered that picture. It revealed that space and time are not separate, but are fused into spacetime, and that spacetime itself can warp. Massive objects like planets and stars create dents in this fabric, and those dents are what we experience as gravity. This means you, Dan T, fall toward the Earth because there, as an invisible force pulling you, you fall because space-time is curved. And you're simply following its curves. Think about that. Every step you take, every time you drop something, every moment you've ever felt weight, you've been moving through a landscape of invisible curves drawn by the mass of the Earth beneath your feet. And as you sit there, listening to this, time itself is running ever so slightly slower for you than it is for someone far away in deep space. Not by much fractions of a second over a lifetime, but it's real. Astronauts aboard the International Space Station actually age a little differently than you do. The bending of time is called time dilation, and it's been proven again and again. In the 1970s, scientists flew atomic clocks around the world on airplanes, comparing them to identical clocks on the ground. The airborne clocks showed a tiny difference, exactly as Einstein predicted. It's not science fiction, it's science fact. Your GPS navigation in your phone wouldn't even work without correcting for time dilation. The satellites orbiting Earth experience time a little faster than we do on the surface, and their systems have to adjust for that. Without this, your location would be off by miles. So, space and time are not fixed. They're flexible, dynamic, responsive to matter and energy. But they're also slippery to define. If you try to imagine empty space without anything in it, no particles, no light, no gravity, it's still not truly empty. Quantum physics tells us there's always a restless sea of energy bubbling beneath what we think is nothing. Even the vacuum of space hums with the potential for particles to flicker in and out of existence in the blink of an eye. And time is even stranger. Is it a real thing, flowing like a river? Or is it just our way of keeping track of change? Some physicists, like Carlo Rovelli, suggest that time might not be fundamental at all, that it could emerge from the relationships between events. Like the rhythm you hear from the ticking of a clock is not in the gears themselves, but in how they move relative to each other. Others, like Julian Barber, go further, proposing that time doesn't flow at all, every moment simply exists. And our perception of movement from past to future is a trick of memory. This idea is unsettling, because our lives are built on the idea of before and after. You woke up before you started listening to this. After this, you might go to bed or go to work. But what if all those moments, your birth, this instant, your future self, are all equally real, all happening in some timeless structure of reality? If so, then the now is just one slice of a far bigger picture. It's worth pausing here and thinking about your own life in this light. If time is not what we think, then your past isn't going to knit simply in another part of space-time, and your future. It's already there, waiting for you to arrive. In that sense, life is not a journey through time, it's a journey within space-time, and every place you'll ever be already exists. Daily life hides these truths from us. You walk to the store, you wait in traffic, you watch the seconds change on your phone. You feel like you're moving forward in a straight line. But if you were an observer outside our universe, watching the whole of space-time at once, you'd see not a moving dot, but a glowing thread stretching from birth to death, every moment connected, every point, part of a single unbroken line. And yet, space and time aren't just abstract concepts. They're the stage for our emotions, our memories, our hopes. When you think of a place from your childhood tree you climbed, a road you walked to, not just recalling its position in space, but its position in time. The tree might still be there, but that moment is gone. Or maybe, in the deeper sense, it's still there, waiting in the eternal structure of space-time. The more we learn about space and time, the more the boundary between science and philosophy blurs. We're forced to ask not just what is the universe, but what does it mean to exist within it? When Einstein said, after the death of a friend, that for us believing physicists, the distinction between past, present, and future is only a stubbornly persistent illusion. He wasn't being poetic. He was stating a scientific truth as he saw it. If you stand still and look around, it feels like space is just out there, waiting for you to move through it. You can reach out, touch something, walk to a new location. But the reality, as modern physics sees it, is that space isn't merely an empty container, it's dynamic. It can stretch, bend, ripple, and even expand. This idea became unavoidable when astronomers discovered in the early 20th century that the universe itself is expanding. Edwin Hubble's work showed that galaxies are rushing away from us, and the farther they are, the faster they recede. This wasn't galaxies moving through space like cars on a road, it was the road itself stretching beneath them. Think about that. Space is not a static backdrop, it's an active player. Imagine the fabric of space-time like a vast sheet of rubber. Place marbles on it, and they create dimples. Roll another marble nearby, and it curves toward the dip. Not because the marble pulled it, but because the surface itself is warped. Now imagine the sheet itself is slowly stretching in every direction, This is cosmic expansion. On the grandest scales, galaxies are not simply moving away from each other. Space is being created between them. This has a strange implication. There is no universal center of the universe. Every point in space can think of itself as the center, because everything sees everything else moving away. It's like dots on the surface of an inflating balloon, no matter which dot you stand on. All the others are moving away from you as the balloon expands. And here's where time joins the conversation again. The expansion of space is tied to the history of time itself. If you run the cosmic movie backward, galaxies get closer together, space contracts, and you eventually arrive at a moment about 13.8 billion years ago, the Big Bang. But the Big Bang wasn't an explosion in space. It was the birth of space and time themselves. Before it, there was no before in the conventional sense, because time as we know it didn't exist. Asking what happened before the Big Bang is like asking what's north of the North Pole. Our current physics says the question may not even make sense. Of course, that doesn't stop scientists from exploring possible answers. Some theories suggest there could have been a before in a deeper, hidden framework of reality, perhaps a prior universe, or an eternal cycle of expansion and contraction. Others think that time might have emerged from something timeless, a quantum state beyond our current imagination. Physicists like Sean Carroll and Alan Guth explore models in which our universe could be just one bubble in an eternal cosmic foam. But even within our universe's lifetime, space and time behave in ways that defy common sense. Take black holes, for example, regions where space-time is curved so extremely that not even light can escape. To an outside observer, time near a black hole slows almost to a standstill. If you were to watch a spacecraft fall toward the event horizon, you'd see it move slower and slower until it appeared frozen at the edge forever. From the astronaut's perspective, however, they'd cross the horizon without noticing anything unusual at that moment, though their fate would be sealed. Daily life seems a million miles away from such extremes, but in truth, these same principles are at work here and now. When you climb a mountain, time ticks a tiny bit faster at the top than at the bottom, because you reach farther from Earth's center of gravity. You won't notice it, but precise instruments can measure it. That means if you live your life at sea level and I live mine in the mountains, we'll age at slightly different rates in effect so small that only modern physics could uncover it. Space and time also reveal themselves in the motion of light. Light always travels at the same speed in a vacuum, about 299,792 kilometers per second, no matter who measures it or how fast they're moving. This constancy forces space and time to adjust themselves to keep the speed of light fixed. If you move very fast, distances contract and time slows for you relative to someone at rest. This is not a perception. It's a measurable, physical reality. That's why high-energy particles from space, called muons, can survive far longer than they should when moving near light speed toward Earth's surface. Their internal clocks tick slower. The relativity of time is not just a mathematical curiosity. It's a direct challenge to our everyday experience. In your daily life, you trust that now is a shared reality. But physics suggests that simultaneity is relative. Two events that happen at the same time for you might happen at different times. For someone moving differently through space-time, there's no universal now slicing across the cosmos. Every observer carries their own personal map of time. If you think about it long enough, this is deeply liberating. It means reality is richer and more complex than our human habits of thought allow. It means that the story of the universe isn't just a single unfolding thread, but an intricate weave of countless threads each observer's path through space-time. When we step back and consider this, space and time stop being background scenery and become active ingredients in the cosmic recipe. They're not passive. They interact with matter and energy, respond to it, and in turn, shape it. The presence of matter tells space-time how to curve. The curvature of space-time tells matter how to move. That elegant phrase, attributed to physicist John Archibald Wheeler, captures the dance perfectly. And what's more, quantum mechanics adds another twist. At the smallest scales, space and time themselves might not be continuous. They might come in discrete quanta, just as energy does. This is the realm of quantum gravity, a still unsolved puzzle where researchers like Carlo Rovelli, Lee Smolin, and Juan Maldacena explore ideas like loop quantum gravity or holographic spacetime. In some versions of these theories, space emerges from entanglement, the quantum connections between particles. This would mean that space itself is not fundamental, but a kind of network woven from relationships. The possibility that space and time could be emergent rather than fundamental changes everything. It suggests that the universe we experience could be like a projection from deeper laws, just as a 3D hologram emerges from a flat surface. If that's true, then what we think of as moving through space might be more like navigating the relationships in an underlying quantum network. And yet, for all its strangeness, this reality is still the one you wake up to every day. You drive down roads laid out on a spinning planet. You make plans for the future. You look back on the past. Even though physics tells us that space can warp and time can slow, we live in a local bubble where the rules feel steady. That SY exploring space and time, ISNT. Just about exotic cosmic phenomena. S about realizing that even the most ordinary moment in your life is part of an extraordinary fabric. When you start thinking about space and time as part of one unified structure space, you begin to realize that every event in the universe has a unique address. That address isn't just a location in space, like X, Y, Z, but also includes a time coordinate T. Imagine plotting your life on this four-dimensional grid. Right now, as you read these words, you occupy one specific point in spacetime that will never exist again. The moment will pass, and you'll move to a new point. Everything you do is a journey through this cosmic coordinate system. One of the strangest consequences of this view is that past, present, and future all exist in the structure of spacetime. This concept, sometimes called the block universe model, suggests that all moments are equally real, like pages in a book. You're simply reading them in order. In this perspective, the flow of time is more about our perception than about an objective property of the universe. This idea has philosophical as well as scientific implications. If all moments exist, does that mean the future is already set? Or is there room for genuine novelty and choice? Physicists and philosophers debate this fiercely. Einstein himself famously wrote in a letter that for those who believe in physics, the separation between past, present, and future is only a stubbornly persistent illusion. It's tempting to think of time as an unstoppable river carrying us along, but relativity hints that we're more like travelers choosing paths through a landscape. Your speed, your gravity, and your trajectory all determine how your clock ticks relative to others. This has been experimentally confirmed many times. Atomic clocks flown around the world on airplanes tick at different rates compared to those left on the ground. Even GPS satellites must account for these differences, both from their speed, special relativity, and from their weaker gravity, compared to Earth's surface general relativity. Without these corrections, GPS would drift kilometers out of alignment within a single day. The fact that our everyday technology already needs Einstein's theories to function should make it clear space and time are not abstract curiosities. They are part of the infrastructure of reality, and we are constantly interacting with them. And yet, despite how much we've learned, the nature of time remains one of the deepest mysteries in physics. Why does time seem to have a direction? The laws of physics mostly work the same forward or backward, but our experience is one way. We remember the past, not the future. Eggs break, but don't unbreak. This arrow of time seems to be linked to entropy, tendency of systems to evolve from order to disorder. In the early universe, everything was in an extremely ordered, low-entropy state. As time passes, entropy increases, giving rise to the irreversible processes we experience. In daily life, entropy explains why your coffee cools down if you leave it on the counter, but never spontaneously heats up. It's why you can't unmix cream from coffee once it's stirred in. These processes are so familiar that we rarely question them, but they read deeply connected to the structure of time itself. If the universe had started in a high-entropy state, perhaps time wouldn't have the same arrow we experience now. Some scientists speculate that in certain extreme scenarios, like inside a black hole or in the very distant future, time's arrow could behave differently. And speaking of the far future, space and time also dictate the ultimate fate of the cosmos. If the expansion of the universe continues to accelerate, as current evidence from dark energy suggests, then galaxies will eventually disappear beyond each other's horizons. Over trillions of years, stars will burn out. Black holes will evaporate through Hawking radiation. And the universe will become a cold, dark, and thinly spread expanse of heat death. In such a state, time may lose its meaning because nothing will change in any noticeable way, but alternative possibilities remain. If dark energy changes over time, the expansion could slow or even reverse, leading to a big crunch where the universe collapses back in on itself. There are even models where the universe rebounds in a cycle of bangs and crunches, each resetting space and time in an eternal rhythm. Roger Penrose has proposed a more radical vision, conformal cyclic cosmology, in which the infinite future of one universe becomes the Big Bang of the next, with space and time flowing seamlessly between them. On the smallest scales, the quantum world refuses to give us a final answer about what space and time really are. Quantum field theory treats space and time as a fixed stage where particles interact. But when you add gravity to the mix, the stage itself becomes part of the quantum drama. In some approaches, space-time emerges from something even more fundamental: patterns of information or entanglement. This would mean that the geometry of space is not a given, but is built from the relationships between quantum states. It's as if reality is a vast network and distance. It's just a way of describing how connected different parts of the network are. For example, the holographic principle, inspired by black hole physics and developed by thinkers like Gerard T. Hooft and Leonard Susskind, suggests that all the information contained in a region of space can be described by data encoded on its boundary. If this principle holds true universally, our three-dimensional world could be a kind of projection from two-dimensional data on a cosmic horizon. It's a mind-bending possibility that space, as we know it, isn't truly out there, but is a construct emerging from deeper laws. Even if this turns out to be the case, it doesn't make your daily walk through the park any less real. Just as pixels on a screen create the illusion of depth in a video game, the emergent space of our universe is the reality we inhabit and navigate. But it does mean that at the deepest level, our intuitive sense of space and time might be as incomplete as a flatlander's understanding of height. This leads to a humbling conclusion. What we call space and time may be useful concepts for our human scale experience. But in the grand scheme of physics, it could be approximations, like the idea of solidity in a table that is mostly empty space at the atomic level. Reality might be stranger, richer, and more layered than our current language can express. And yet, by studying space and time, we come closer to seeing the architecture of existence itself. When you look up at the night sky, the light you see is a message from the past. The moon's glow left its surface just over a second ago. Sunlight takes about 8 minutes to reach us. Light from the nearest star beyond the sun, Proxima Centauri, has traveled for more than 4 years. And a faint glimmer from the Andromeda Galaxy set out on its journey more than 2 million years ago, before Homo sapiens even existed. This means that your eyes are time machines, letting you peer into history. Space and time are inseparable in this way. Looking farther means looking back in time. Astronomers often speak in terms of light years, which is the distance light travels in 1 year, about 9.46 trillion kilometers. This unit blends space and time into one measure. If you hear that a galaxy is 100 million light years away, That also means you are seeing it as it was 100 million years ago. In that sense, our entire picture of the universe is an ancient snapshot. The present moment on a cosmic scale is something we can never truly see. This time delay has a strange implication. Somewhere out there, an alien civilization could be watching Earth as it was thousands or millions of years ago. They might see dinosaurs roaming lush forests or early humans learning to control fire. And if we could see them in real time, they might already be gone, or they might not yet have evolved. It's as if the universe is a vast library of moments, but we can only check out books from the sections light has had time to reach us from. The way space and time are linked also means that traveling across the cosmos is not like taking a road trip. Even at the speed of light, the ultimate cosmic speed limit, you could circle Earth 7 times in a second, but it would still take over 4 years to get to the nearest star. Human lifetimes and cosmic distances are vastly mismatched, which is why science fiction often imagines bending or folding space-time itself to shorten the journey. Einstein's general relativity tells us this is possible in theory. Massive objects curve space-time, and light follows that curvature. This is why light from distant galaxies can be bent around massive clusters of galaxies between us and them, a phenomenon called gravitational lensing. We've used this effect not only to discover new galaxies, but also to map dark matter, the mysterious substance that makes up most of the mass in the universe. But doesn't emit or absorb light. In a sense, gravitational lensing is nature's own telescope. By studying how much and in what way the light is bent, astronomers can infer the distribution of mass in the lensing object. This kind of cosmic detective work blends our understanding of space and time into a powerful tool for uncovering hidden parts of the universe. But bending space-time raises tantalizing possibilities beyond astronomy. If we could manipulate space-time in controlled ways, we might create shortcuts between distant points, wormholes. The mathematics allows for such structures, and physicists like Kip Thorne have explored what they might require. The challenge is that keeping a wormhole stable seems to demand exotic matter with negative energy density, something we have no evidence for on usable scales. Still, the very fact that the laws of physics outright forbid such paths keeps the idea alive in both scientific research and popular imagination. Daily life rarely forces us to confront the relativity of space and time, but the principles are there in subtle ways. When you use your smartphone to navigate, you are relying on GPS, satellites that constantly adjust their clocks for both the slower ticking caused by their speed and the faster ticking caused by their position. Higher in Earth's gravitational field. The corrections are small nanoseconds, but without them, positioning errors would accumulate quickly. In just a single day, your GPS location could be off by kilometers. This is relativity, not as a thought experiment, but as an everyday necessity. The interplay between space and time also influences how we understand motion and rest. In Newton's view, you could speak of absolute space and absolute time in changing backdrops against which everything happens. But in relativity, these absolutes vanish. There is no single rest frame that defines the universe. All motion is relative to something else. This means that space and time coordinates depend on who's measuring them and how they are moving. For example, imagine 2 people, one on a train moving near the speed of light, hypothetically, and one standing on the platform. If they both measure the length of the train and the timing of events inside it, they will not agree. To the person on the platform, the train is shorter length contraction, and the clocks inside tick more slowly, time dilation. To the person on the train, it's the outside world that is length contracted and time dilated. Both are correct in their own frame of reference. This is not just an illusion. It's a real difference in how space and time are experienced. At human speeds, these effects are vanishingly small, but in particle accelerators, they are everyday realities. Subatomic particles moving close to light speed can live thousands of times longer than they would at rest. This is how scientists can study particles that would otherwise decay in a fraction of a second. Space and time stretch for them in ways our everyday senses can't detect, but our instruments measure with precision. In the quest to unify our understanding of space, time, and the other forces of nature, physicists are trying to merge general relativity with quantum mechanics. This is one of the biggest open problems in science. Relativity handles the large-scale structure of space-time beautifully, while quantum theory rules the subatomic world. But when you try to apply both to the same situation, like the singularity inside a black hole or the earliest instant of the Big Bang, the equations break down. This hints that our current ideas about space and time are incomplete. Some proposals, like loop quantum gravity, suggest that space-time is not continuous, but made of discrete atoms of space and time at the Planck scale, far smaller than anything we can currently measure. In this view, the smooth fabric we perceive is like the surface of a painting, which under a microscope reveals individual brushstrokes. Other approaches, like string theory, propose that the basic building blocks of reality are tiny, vibrating strings whose vibrations create not only particles, but also the geometry of space-time itself. What's striking is that no matter the theory, space and time emerge as dynamic, flexible, and deeply intertwined with matter and energy. They are not mere settings for the universe. They are part of the cast. This perspective transforms the way we think about our own existence. We are not separate from space and time. We are woven into them. Our bodies, our thoughts, our histories all are patterns in this vast four-dimensional tapestry. The more we learn, the more space and time seem less like independent arenas and more like expressions of deeper laws. Laws we may not yet have the language to fully describe. Every step toward understanding them is also a step toward understanding why the universe is the way it is, and why we are here to ask these questions at all. The universe isn't just vast in size at S, also vast in its variety of ways to experience and measure it. One of the mind-bending concepts that physicists like Hermann Minkowski and Albert Einstein helped us understand is that space and time form a single fabric called space-time. This isn't just poetic language, it's a literal framework that changes the way events unfold depending on speed, gravity, and position. Imagine throwing a pebble into a pond. The ripples expand outward, but if the water were thick and elastic, a heavy ball dropped in would create a dent that the ripples had to curve around. In space-time, mass is like that heavy ball. It tells space how to curve, and space tells objects how to move. This is why planets orbit stars and why light bends near massive objects. The path is curved because the fabric itself is bent. Now here's where things get more personal. That same curvature means that time itself can run differently depending on where you are. For example, if you were standing at the base of a mountain and your friend stood at the top, your clock would tick more slowly than theirs because you are deeper in Earth's gravitational field. The difference is incredibly tiny in daily life, but it's measurable with atomic clocks. The GPS system corrects for this effect constantly to keep our navigation precise. Thinking about this makes now feel like a slippery concept. In relativity, simultaneity is not absolute. It depends on your frame of reference. Two events that are simultaneous for you might occur at different times for someone moving relative to you. This challenges our common sense, which evolved in a world where speeds are low compared to light and gravitational differences are tiny. In the cosmic realm, our intuitions need rewriting. We can take this further by looking at what happens when space-time is warped to extremes, like near a black hole. The stronger the gravity, the more space-time curves, and the more time dilates. For an observer falling toward a black hole, their own time feels normal. But to a distant observer, their fall slows and appears to freeze at the event horizon. The signals they send out take longer and longer to arrive, stretched into invisibility by gravitational redshift. From far away, it's as though they never quite cross over. These effects aren't just theoretical curiosities, they're built into the mathematics of general relativity, which has passed every test we've thrown at it for over a century. In fact, scientists like Arthur Eddington confirmed Einstein's predictions as early as 1919. When they measured the bending of starlight around the sun during a solar eclipse, it was a watershed moment in physics, showing that our ideas of space and time needed a radical update. The idea that space and time are linked also gives rise to one of the most fascinating concepts in modern physics: space-time diagrams. These are ways of mapping not just where and when something happens, but how light cones define the possible past and future of an event. Your light cone contains everything that can possibly affect you and everything you can possibly affect, bounded by the speed of light. Outside that cone are regions of space-time that are forever causally disconnected from you, places and events you can never reach or influence. This is not science fiction, it's geometry. And yet, even with these limits, the structure of space-time is not static. The universe is expanding. Discovery made by Edwin Hubble in the 1920s and confirmed in ever more detail since. This expansion means that distant galaxies are moving away from us, and the farther away they are, the faster they recede. Eventually, light from some galaxies will never reach us, because the expansion is carrying them beyond our cosmic event horizon. This means our observable universe is finite in time, as well as space, are constantly changing bubble inside an even larger reality. In daily life, we almost never think about these boundaries or warps, but they subtly influence our perspective on existence. Your morning commute happens within a gravitational well shaped by Earth's mass. And your heartbeat keeps pace in a rhythm defined by space-time's local curvature. Even the simple act of looking at a loved one's face involves photons that traveled through the geometry of space to reach you, geometry shaped by every particle of matter around. Some thinkers, like Carlo Rovelli, suggest that space and time themselves might be emergent phenomena, things that arise from more fundamental processes. Like temperature arises from the motion of atoms. In this view, what we think of as the continuous flow of time might be an approximation, a large-scale behavior emerging from microscopic interactions. If this is true, then space and time as we know them are not ultimate realities, but part of a deeper layer of physics yet to be uncovered. Every time we send a probe into deep space or detect gravitational waves from colliding black holes, we're not just gathering data about distant phenomena, we're testing the very nature of reality. Those ripples in space-time detected by LIGO in 2015 were changes in the geometry of the universe passing through Earth, caused by two black holes merging over 1 billion light-years away. In that moment, we didn't just observe the universe, we felt it move. So here's something I want you to imagine. You're lying down, maybe in your backyard, maybe somewhere far from the city where the air smells fresh and the Milky Way paints a stripe of light above you. You look up, and without even trying, your mind starts traveling. That glow you see isn't just a bunch of random dots. It's light that has been traveling for thousands, sometimes millions, of years to get here. You're not looking at now in space, you're looking at then. Every star is a time capsule. This is where the weirdness starts to sink in space, and time are tangled together in such a way that the farther we look, the further back in time we see. And here's the mind twist. That means there is no true present for the universe as a whole. Your present is yours alone, shaped by your position in space and your motion through it. The universe doesn't have a single clock, it has billions of them, each ticking at its own pace. Now let's bring this down to Earth, literally. If you've ever been on a plane for a long-haul flight, you've actually aged slightly less than people who stayed on the ground. We're talking nanoseconds, sure, but this isn't theory. It's a measurable effect called time dilation. The faster you move, the slower your clock runs relative to someone stationary. Astronauts on the International Space Station, zipping around at 17,500 miles per hour, experience this too. They come back just a fraction younger than we do down here. When you realize that time can stretch or compress depending on speed and gravity, The old idea of a universal time feels as outdated as believing the Earth is flat. Einstein's relativity forces us to see time as flexible, as something that flows differently for different observers. And yet, our daily routines, morning coffee, lunch breaks, deadlines, are all built on the illusion that time ticks the same for everyone. Speaking of illusions, here's a question. Is time something that flows, or something we move through? Imagine a DVD of your favorite film. Every scene of the movie exists on that disc all at once. The difference between past, present, and future is simply the part you're watching right now. Some physicists think the universe might work in a similar way, that all moments exist together. And what we call now is just the frame our consciousness is experiencing. That idea is called the block universe theory. It's unsettling, but also strangely comforting. If every moment exists forever, then nothing is ever truly lost. It's all still there, somewhere in the fabric of space-time. I can't help but think how that changes the way we value experiences. If a perfect moment to sunset with someone you love or the laughter of your child still exists somewhere in space-time, maybe it's not gone when the clock moves on. Maybe it's just stored in a part of the universe we can't reach again. Let's zoom back out to the cosmic scale. Edwin Hubble discovered that distant galaxies are rushing away from us, which means the universe is expanding. But here's the twist. This expansion stretches space itself, which means the fabric of space-time is growing between galaxies. Light traveling across that fabric gets stretched too, shifting toward the red end of the spectrum, which is how we measure how fast a galaxy is moving away. This is called redshift, and it's like a Doppler effect for light. Now, imagine you're floating in deep space, far from any galaxy. Your sense of here and now would still be completely local. You wouldn't feel the expansion happening. That S because expansion ISNT, a wind or a force pushing galaxies apart TIT, a very geometry of the universe changing underneath them. And that, my friend, is where space and time stop feeling like empty backdrops and start feeling like living characters in the story of the cosmos. They bend, stretch, ripple, and warp in response to what happens inside them. You and I, right now, are sitting in the middle of that story, inside a bubble of space-time shaped by Earth's mass. The sun's pull, the Milky Way's gravity well, and the expansion of the universe beyond. The cool part: the same physics that explains all this also predicts things that sound impossible, like wormhole shortcuts through space-time that could, in theory, connect distant parts of the universe instantly. We don't know if they actually exist in a usable form, but the equations don't forbid them, and if they do, well, that's a whole other road trip through the cosmos waiting to happen. If you're still with me here, think about this. Every step you take is a journey through both space and time. You can't move through one without moving through the other. And maybe, just maybe, that means that every choice you make sends you down a unique path through the cosmic map, one that no one else will ever walk in quite the same way. Picture this. You're walking through your neighborhood at sunset. The air is cool, the light is golden, and shadows stretch long across the pavement. You feel like you're in the present, but you're actually moving through both space and time. Every step shifts your position in the universe and moves you forward on your personal timeline. That's the ordinary, everyday version of space-time travel, but underneath it, something extraordinary is happening. The atoms in your body are constantly vibrating, the electrons buzzing with quantum energy. Your heart is beating thanks to a delicate electrical rhythm. And your brain is firing patterns of neural activity that are themselves subject to the laws of relativity and quantum mechanics. You're not just in space, you are space. The particles that make you up were forged in stars billions of years ago. This means you're walking through the street wearing a body made of ancient stardust. And here's where time plays a trick. Those atoms have existed for eons, but they rearranged in a way that is uniquely you for only a fleeting moment in cosmic terms. It's strange, isn't it? We measure our lives in decades, but in the cosmic clock, Even the entire history of humanity is a blink. Dinosaurs ruled Earth for 165 million years. We've had smartphones for barely 2 decades. And yet, in that brief window, we've discovered that time isn't universal and space isn't fixed. Newton saw the world as a grand stage. Space was the arena, time was the clock, and everything moved within them. Einstein flipped that completely. The arena is alive, bending and stretching depending on what's in it. Imagine throwing a heavy bowling ball onto a trampoline. That curve you see is exactly how space bends when something massive like the Earth or the Sun is present. Drop a marble onto that trampoline and it rolls toward the bowling ball, not because there's an invisible force pulling it, but because the marble is following the curve in the fabric beneath it. That's gravity. Not a pull, but the geometry of space-time telling matter how to move. Now, here's where it gets even weirder. Space can bend so much that time itself is affected. Stand near a massive object, say, the surface of a neutron star, and your clock will tick slower than someone far away from it. This isn't science fiction. It's been measured on Earth using extremely precise atomic clocks. Put one clock at sea level and another on a mountain, and the mountain clock will run ever so slightly faster because it's in weaker gravity. What does this mean for you and me? It means that the concept of now is slippery. Your now and mine are slightly different depending on where we are and how we're moving. In a way, every person is carrying their own personal timeline through the universe. This is called the relativity of simultaneity. Events that seem simultaneous to you might not be simultaneous to someone moving differently through space. Think about the last time you called someone in a different time zone. You said good morning, and they said good night. That's the simple human version of it. But at a cosmic scale, two events separated by great distances might not even agree on which happened first, depending on the observer. Time isn't a straight road, it's a network of paths that weave through the universe. And this brings us to one of the most mind-bending questions in physics. Is time something that emerges from the universe's structure? Or is it something fundamental? Some physicists think time might not be real in the way we think it. Is that it's more like a measure of change, a side effect of the way events are ordered? If that's true, then our experience of past, present, and future might be more about perception than reality. Daily life is full of little reminders of this. Watch a slow-motion replay of a hummingbird hovering. In real life, its wings move so fast they re-blur but slow it down and you see each precise beat. That's not changing reality. It's changing your frame of reference. Physics says the same thing happens in the real world. Different observers have different frames of reference for time itself. Space plays a similar trick on us. We tend to think of it as empty, a backdrop. But quantum physics tells us it's not empty at all, lit as a seething field of energy, with virtual particles popping in and out of existence all the time. Even empty space has structure, and that structure affects how things move and interact. This is why light can be bent around massive objects' gravitational lensing, and why the universe has a cosmic microwave background, a faint afterglow from the Big Bang that fills space everywhere. Here's a thought experiment. Imagine freezing the universe in place, like pressing pause on a movie. Every particle, every beam of light, every galaxy, frozen. What would time even mean in that frozen universe? If nothing changes, there's no way to measure it. In that sense, time is tied to change. Without motion or change, time loses its meaning. But of course, the universe never stops. Galaxies spin, stars are born and die, black holes merge, and here on Earth, you blink, breathe, and think. Every one of those changes is a step forward in your personal journey through space-time. You can never go backward along your timeline, at least. Not with the laws of physics as we currently understand them. That hasn't stopped people from imagining it. Science fiction loves the idea of time travel, but physics puts strict limits on it. Traveling forward is easy. We do it all the time, and relativity says we can speed it up by moving faster or sitting in stronger gravity. Traveling backward, that's where paradoxes pop up, like the famous grandfather paradox, where you might prevent your own existence. Some solutions in theoretical physics, like closed time-like curves, suggest it might be possible under certain exotic conditions, but we're a long way from proving nor. Disproving nor. Disproving nor, nor. My se. Supplosing nor. My nor. I build it to sive. I can mean nor. My nor. I call it. Come on nor. Nor. It is it doc at. By we so sorry to me I be lights to sit it by I sit dosi you could bit it's a sit it law I by that be sit with it the sick case. That's to another blackers that just sits about the second of the work I guess the best I believe I Still, thinking about these things changes how you see the present moment. Space and time aren't separate, they're one fabric, and we're woven into it. Every breath you take, every glance you cast at the night sky is part of a vast, connected tapestry stretching from the birth of the universe to its distant future. Think about the night sky, the last time you saw it without city lights, maybe on a camping trip or out in the countryside. Those countless stars. Some of them might not even exist anymore. Their light has traveled for thousands or even millions of years to reach you, and in that time, the star itself could have burned out or exploded in a supernova. You are literally looking into the past every time you look at the cosmos. That's the daily life proof that space and time are inseparable. Distance in space is also distance in time. If you glance at the moon, you're seeing it as it was about 1.3 seconds ago. Look at the sun, and you're seeing it as it was over 8 minutes ago. Look at the Andromeda galaxy, and you're seeing light that's been traveling for over 2 million years. That's not a poetic metaphor, that's literal physics. In a sense, telescopes are time machines. They can't take you forward or back in your own life, but they let you witness moments from the deep past. This is part of what Einstein's theory of relativity formalized. The speed of light is a constant in the universe, and nothing can travel faster than it. That cosmic speed limit is the reason time and space are tied together. If you could somehow exceed that limit, you'd be able to mess with causality, seeing effects before causes. But nature seems to have built-in safeguards against that. Now, let's zoom in from cosmic distances to something closer to home. GPS, the thing that lets your phone tell you exactly where you are, is a direct proof that relativity matters in daily life. The satellites in orbit are moving fast and are further from Earth's gravity, so their clocks tick slightly faster than clocks on the ground. Engineers have to correct for both special relativity due to motion and general relativity due to gravity to keep GPS accurate. Without that adjustment, your phone's map could be off by kilometers. So even if you never think about space-time, it's guiding you home every day. But there's a deeper mystery. What exactly is space? Is it a physical thing, a fabric that can stretch and bend, or is it simply a set of relationships between objects? Philosophers like Leibniz argued that space is relational, only existing as distances between objects, while Newton treated it as an absolute stage where events happen. Modern physics tends to treat it as a dynamic entity. Quantum fields fill it, gravity shapes it, and dark energy stretches it. Dark energy, now there's a wild one. We discovered it in the late 1990s when astronomers measured distant supernova and found that the universe's expansion is speeding up. That's the opposite of what gravity should be doing. It's as if space itself has an energy that pushes galaxies apart. And here's the kicker. Dark energy makes up about 68% of the universe, yet we don't know what it is. Dark matter, which holds galaxies together, adds another 27%. That means everything we see, stars, planets, you, me's, just 5% of what exists. And time. Time is even trickier. We feel it as a flow, a one-way arrow from past to future. But the fundamental equations of physics don't actually require that arrow. They work just as well backward as forward. So why do we experience time moving in only one direction? The most accepted answer comes from entropy, the tendency for systems to go from order to disorder. You can break an egg and make an omelet, but you can't easily turn the omelet back into a perfect egg. That one-way increase in disorder gives us the arrow of time. Every breath you take increases entropy. Every memory you form is your brain recording events in an irreversible way. That's why you remember the past, but not the future. The processes that store those memories are tied to entropy zero. But here's a thought. From a block universe perspective where past, present, and future all exist equally, you do exist in the future, just as you exist in the past. You're simply experiencing one slice at a time. Daily life is full of tiny relativity experiments. Ever noticed how time feels different depending on what you're doing? An hour stuck in traffic feels endless, but an hour laughing with friends flies by. That's psychological time, and while it's not the same as physical time, it's a reminder that our experience of the universe as most fundamental dimensions is filtered through our minds. Physics has its own thought experiments about this. Einstein's famous twin paradox imagines one twin traveling near the speed of light and returning younger than the other. That's not just theory, it's been tested with high-speed jets and particle accelerators. Time dilation is real. So in a way, the fastest route to the future isn't waiting at S, moving fast, or hanging out near massive objects. And then there's quantum physics, which throws another wrench into the picture. At the quantum scale, particles don't have definite positions or velocities until measured. They exist in probabilities. Space and time at that level might not even be continuous, but made up of tiny, discrete units. Some theories, like loop quantum gravity, suggest space-time itself could be quantized. If that's true, then the smooth fabric we imagine might be more like a woven cloth when you zoom in threads of space and time. Now imagine if space and time aren't fundamental at all, but emerge from something deeper, like patterns of entanglement between quantum states. This is a leading idea in some corners of theoretical physics, that space-time might be the large-scale illusion produced by more fundamental building blocks we haven't yet fully grasped. Which leads to the ultimate question: if space and time aren't fundamental, what is? And if the universe had a beginning, say, the Big Bang, what was before space and time? The honest answer from physics is, the question might be meaningless, because before assumes time existed to measure it. It's like asking what's north of the North Pole. We've only scratched the surface here, but the deeper we dig, the more space and time stop being background and start being active participants in the story of the universe. Imagine holding two identical atomic clocks, one on the ground floor of a skyscraper and one on the top floor. The one higher up, just a few dozen meters above, ticks slightly faster because it's in a weaker gravitational field. This isn't science fiction, it's been measured with mind-boggling precision. That's general relativity at work. Gravity doesn't just pull on mass, okay? It bends time itself. Your head is technically aging faster than your feet right now. The effect is tiny, but it's there. Now, zoom out to the cosmos. Around black holes, this warping of time becomes extreme. To a distant observer, anything falling toward the event horizon seems to slow down infinitely, never quite crossing over. But for the falling object, time ticks normally until it's gone. This time stretching is not only a mind-bender, but it's also a reminder that time is not the same for everyone, local and personal. The universe has no single now that applies everywhere. That fact alone can shatter our everyday intuition. We tend to think of the present as something universal, a giant slice of existence we all share. But according to relativity, your present might not line up with someone else's if they, removing differently or in a different gravitational field. Two events that are simultaneous for you might happen in a different order for someone else. Reality is a lot less absolute than our senses suggest. Let's step back into history for a moment. Before Einstein, time was thought to be a uniform river, flowing the same for everyone, everywhere. Isaac Newton treated it as an absolute background, like a cosmic metronome. Then along came Einstein's special relativity in 1905, merging time and space into a four-dimensional space-time. And 10 years later, with general relativity, showed that space-time isn't fixed, it's dynamic, curving in response to matter and energy. This idea was radical, but experiment after experiment has proven it correct. Still, Einstein wasn't the end of the story. Quantum mechanics came along, showing us a universe full of uncertainty and probabilities. And here's where the tension begins. General relativity treats space-time as a smooth, continuous fabric, while quantum physics suggests that everything might be made of discrete quanta. Trying to unify these two views is one of the great challenges in physics today. Some researchers think the solution might be holographic. Our three-dimensional universe could actually be a projection from information encoded on a distant, two-dimensional boundary. This holographic principle comes from work by physicists like Gerard T. Hooft and Leonard Susskind, building on black hole thermodynamics. If true, then space itself is emergent, like a 3D image emerging from a flat hologram. That would mean our most basic notions of distance and location are just convenient illusions. You might wonder how this connects to your daily life. Well, here's one angle. If space and time are emergent from something deeper, say, from quantum entanglement, then everything in the universe is linked at a fundamental level. When you move, think, or even breathe, you're part of a vast, interconnected web. The space between you and someone on the other side of the planet might not be a true gap at all in the ultimate fabric of reality. And the strange truth is, you've already experienced hints of this interconnection. Ever been in sync with someone far away thinking of them just before they message you? That might be pure coincidence. Or maybe, on some level, the universe is more interconnected than classical physics admits. While science doesn't confirm telepathy or mysticism, quantum mechanics does tell us that particles can share a state instantly across vast distances of phenomenon. Einstein himself called spooky action at a distance. We can also turn this exploration into a mental time machine. Picture standing in a field, watching the sun set. That sunset is already over by the time you see it. 8 minutes have passed since those photons left the sun. Look at the stars above, and you're mixing together light from thousands of years ago. Some of those stars may have died long before humans walked the earth. You are quite literally bathed in the history of the cosmos every time you look up. And here's another everyday example. When you listen to someone speaking in a large stadium, the sound you hear is delayed compared to the light from their lips moving. Your brain stitches these together seamlessly, so you perceive them as simultaneous. That's a microcosm of what relativity tells us. The universe is full of delays, perspectives, and distortions, but our minds smooth it all out into a coherent reality. The real question becomes, if space and time are this strange, why do they feel so ordinary? The answer might be evolutionary. We evolved brains that work well for hunting, farming, and building tools, not for perceiving relativistic effects or quantum fluctuations. We see the universe at human scales, and that smooth, intuitive picture has served us well, until we start to explore beyond our everyday world. The deeper you go into physics, the more it seems like space and time are not the foundation, but the stage props. The real play might be happening in a realm of mathematics, quantum states, or even something beyond our current imagination. Yet here we are, tiny creatures living out our days in a slice of space-time, feeling it flow and stretch around us, never fully aware of its true nature. Think about a GPS system in your phone or car. It's easy to forget that it's a marvel of Einstein's theories in action. Those satellites orbiting Earth have clocks that tick at a slightly different rate than your phone. S clock because they both moving relative to you, special relativity, and sitting in a weaker gravitational field, general relativity. Engineers have to correct for these differences as about 38 microseconds a day otherwise. GPS would drift by kilometers every single day. That means every time you navigate to a coffee shop, you're using one of the most accurate and everyday applications of relativity without even realizing it. But the real rabbit hole begins when we ask, what is time, really? Is it something that flows, or is it just a measure of change? Philosophers like Augustine of Hippo puzzled over this long before physics existed. He famously said, "What then is time? If no one asks me, I know. If I wish to explain it to one that asks, I know not." And in the 20th century, Einstein's block universe model where past, present, and future coexist in a static 4D spacetime threw a philosophical grenade into the idea of now. In the block universe view, time doesn't flow. All moments are equally real. The sensation of passing time might just be your consciousness moving along your world line, like reading frames in a film reel. For someone driving a truck across the desert or sitting quietly by a river, it feels like there's a moving present, but in physics, there might only be a frozen spacetime with you experiencing slices of it one after another. Yet quantum mechanics muddies this clean picture. In the quantum world, events are described by probabilities until they're observed. Does this mean the future is open, or is it still fixed like the past? Some interpretations, like the many worlds theory proposed by Hugh Everett, suggest that all possible outcomes of every quantum event happened just in separate, branching universes. If true, then space and time aren't just a single block, they're an infinite, ever-branching multiverse. Daily life hides these complexities well. You wake up, pour coffee, head to work, maybe call a friend. It all feels straightforward. But zoom in far enough, and your coffee molecules are vibrating with quantum uncertainty. The atoms in your body are mostly empty space. And your movement is dragging your personal time along a unique path through space-time. And if you zoom out instead, you find that the space you think of as empty is actually teeming with virtual particles popping in and out of existence. This quantum vacuum energy might even be the driving force behind cosmic expansion, the mysterious dark. Energy pushing galaxies apart faster and faster. Suddenly, nothing becomes a roiling sea of activity, and space becomes a physical player in the universe's story. We can make this even more personal. Imagine you're sitting by a campfire at night. The heat you feel is infrared radiation photons traveling through space and time to your skin. The starlight above you is older than humanity, and the space between you and the stars is expanding even as you watch. You're not a bystander. You're woven into this fabric, moving through it, shaped by it. We could spend years chasing every nuance of what space and time are, from Planck-scale foam to cosmic horizons, and still not exhaust the mystery. But the more you learn, the more you realize that what you experience as ordinary is just the most local, human-scaled tip of something far stranger and deeper. Picture yourself at the edge of a black hole, not close enough to be ripped apart, but close enough that you can feel time itself distorting. For someone far away, your clock seems to slow down, your movements drawn out to a crawl. From your own perspective, time feels normal, but the rest of the universe appears to race ahead. This is gravitational time dilation in action, predicted by Einstein and confirmed by experiments, such as the Pound-Drebka experiment in 1959, and more recently by ultra-precise atomic clock measurements at different heights on Earth. Even a shift of a single meter in elevation can cause measurable differences in the ticking of time. These effects, extreme near black holes, also happen every day. If you live in a tall skyscraper, your head is technically aging ever so slightly faster than your feet. Over your lifetime, the difference is minuscule fractions of a nanosecond, but it's real. The deeper you are in a gravitational well, the slower time runs. Space and time are not passive backdrops. They're dynamic, malleable, and sensitive to the matter and energy around them. The early universe offers another window into how strange they are. Right after the Big Bang, the universe was incredibly hot, dense, and expanding at breakneck speed. Physicists like Alan Guth proposed the theory of cosmic inflation, where space expanded exponentially in a fraction of a second. This explains why distant regions of the universe have the same temperature, and why space looks so flat on large scales. Imagine blowing up a balloon so quickly that any wrinkles are instantly smoothed out. That is inflation in a nutshell. But here's where the daily life connection sneaks in. The very photons hitting your eyes as you read this, or the warmth you feel from sunlight, have traveled through the fabric of space-time shaped by that ancient event. Every sip of water, every breath of air, is made of atoms forged in stars billions of years ago. The expansion of space isn't just a cosmic thing, it's why. On the grandest scale, you will never be able to catch certain galaxies. They are receding from us faster than the speed of light, because space itself is stretching. Now consider the strange boundary called a horizon in spacetime. For black holes, this is the event horizon. Cross it, and not even light escapes. For the universe, there's the cosmic horizon, the limit beyond which light from galaxies will never reach us. You can think of it as a bubble enclosing the observable universe. But here's the kicker. This bubble is always changing. As time passes, more distant light can reach us. Yet at the same time, some galaxies cross beyond our cosmic horizon forever. In that way, space and time themselves decide what parts of reality are accessible to us. Physicists like Carlo Rovelli take these ideas further with loop quantum gravity, suggesting that space might be made of discrete chunks, like pixels in a digital photo, except unimaginably small at the Planck scale. If that's true, then smooth spacetime is just an illusion at our human scale, and underneath it is a granular quantum structure. Compare it to watching a movie on a screen. You see smooth motion, but zoom in far enough, and it's all still frames. And in the quantum world, time becomes even slipperier. The Wheeler-DeWitt equation, for example, describes the universe without any explicit time variable. It hints that time might not be fundamental at all, but rather something that emerges from correlations between events. This idea forces us to ask, if time isn't built into the basic laws of the universe, why do we experience it so vividly? We might answer that with an analogy you can feel right now. Think of listening to your favorite song. The music is made of individual notes, each one still and complete. Yet the meaning and emotion come from the relationship between the notes, from their order. Perhaps time works the same way. It's not about an actual flow, but about the relationships and sequences that our brains interpret as movement from past to future. Imagine yourself in a laboratory the size of 2 continents, the LIGO and Virgo gravitational wave observatories. These instruments are so sensitive they can detect distortions in spacetime thousands of times smaller than the width of a proton. In 2015, for the first time in history, scientists recorded the faint ripple from 2 black holes colliding over 1 billion light-years away. That moment didn't just confirm a prediction of Einstein's general relativity, gave us a new way to sense the universe. Gravitational waves are like cosmic whispers, carrying information about events we could never see with light alone. They let us hear the fabric of space-time being stretched and squeezed. Think of how a pond reacts when you toss in a pebble wave's ripple outward. The pond is space-time, and the pebble is a massive cosmic collision. When these waves pass through Earth, they very slightly change the distance between objects, and we can measure that. Now, take a step back and realize how strange that is. Space itself can expand and contract. Even here on Earth, you are literally surfing on space-time all the time without feeling it. Every GPS satellite in orbit must account for both special and general relativistic effects, because their clocks tick faster due to weaker gravity and their high speeds. They didn't correct for this. Your phone's map would be off by kilometers in a single day. That's relativity in your pocket. The connection between space and time also appears in quantum physics. In experiments like the famous double-slit experiment, particles behave like waves spread out in space, and yet, when observed, they collapse into definite locations. Some physicists, like Hugh Everett with his many worlds interpretation, suggest that all possible outcomes happen, but in different branches of reality. If that's true, then space and time aren't just the stage, they're part of an unimaginably vast, branching structure of possibilities. And yet, from our perspective as conscious beings, space and time feel continuous and unbroken. This might be because our brains evolved to navigate the macroscopic world where quantum effects average out. But deep down at scales we can't sense, there may be no smooth fabric at all, just probabilistic jumps, like pixels flickering on a cosmic screen. In everyday life, we unknowingly interact with these concepts all the time. When you throw a ball, it follows a path determined by both space and time. Its trajectory is shaped by gravity, air resistance, and initial velocity. When you watch a sunset, you're seeing light that has traveled through space for 8 minutes from the sun to Earth. You're always looking into the past, even when staring at the person across from you, because light takes time to travel. But there's another layer, the arrow of time. In physics, most fundamental equations are time symmetrics. They don't care whether time moves forward or backward. Yet, in our lived reality, time always flows forward. This asymmetry is linked to entropy, the measure of disorder, which tends to increase in closed systems. A cup of coffee cools down, but never spontaneously heats up. We age forward, not backward. The arrow of time is, in many ways, the universe's memory of change. Now imagine what happens when we approach extreme conditions inside neutron stars, at the instant after the Big Bang, or at the singularity of a black hole. Here, our best theories break down. General relativity and quantum mechanics give conflicting predictions, and this is why physicists are chasing a theory of quantum gravity. Thinkers like Juan Maldacena, with his holographic principle, suggest that our entire universe might be describable as a projection from a lower dimensional reality. Space and time could be emergent phenomena, not fundamental. And if they're emergent, then asking what is space, what is time is like asking a surfer, what is a wave? A wave is not a thing, it's a process, a pattern in the water. Space and time might be patterns in a deeper, unseen reality. Picture the earliest moments of the universe, fractions of a second, after the Big Bang, when space and time as we know them were still forming. In those unimaginably tiny instants, quantum fluctuations, the random jitter of energy in the vacuum, were stretched by cosmic inflation to enormous scales. These fluctuations became the seeds of galaxies, stars, and planets. That means the vast structure of the universe today is literally a magnified snapshot of quantum randomness from the dawn of time. This link between the smallest scales and the largest is one of the most mind-bending aspects of modern physics. It suggests that space and time are not two separate arenas, but threads in a single tapestry woven from the same fundamental stuff. Einstein's equations tell us how matter and energy bend space-time. Quantum mechanics tells us how matter and energy behave at the smallest scales. But when you try to apply both sets of rules in extreme situations, such as at the center of a black hole, they clash. That's where researchers hunt for a deeper theory. Some physicists look to string theory, which proposes that the fundamental building blocks of reality are not point-like particles, but tiny vibrating strings. Each vibration pattern corresponds to a different particle, and the theory naturally includes gravity. It also implies extra dimensions beyond the familiar 3 of space and 1 of time, dimensions curled up so small we can directly detect them. Others explore loop quantum gravity, which envisions space-time itself as a network of finite loops, like the mesh of a fishing net, giving space and time a quantized structure. While these are bold and mathematically elegant ideas, they're still awaiting experimental confirmation. In the meantime, we can probe the boundaries of our understanding with extreme astrophysical laboratories, neutron stars, quasars, black holes, and with ultra-precise Earth-based experiments like atomic clocks. So accurate, they lose less than a second over the entire age of the universe. These clocks have been used to measure gravitational time dilation over vertical distances of less than a meter, proving again that time really does tick differently depending on where you are. Now, step out of the lab and think about your own perception of space and time. Why does time sometimes seem to fly when you're having fun and crawl when you're bored? Psychologists suggest it's linked to how our brains encode memory. When you experience many novel events, your brain stores more data, and looking back, the period seems longer. Conversely, routine compresses time in retrospect. So in a way, the richness of your experiences stretches your personal space-time. This brings us to a philosophical twist. If space and time are intertwined and subjective at certain levels, perhaps reality itself depends on the observer in deeper ways than we imagine. Niels Bohr famously said, "No phenomenon is a phenomenon until it is an observed phenomenon." And if observers play such a role, then the act of experiencing, whether through science, art, or simply living, becomes part of the universe's unfolding story. Imagine peeling away reality like the layers of an onion. As we strip away the familiar, the solid objects, the air between them, the blue of the sky, we begin to notice that everything we thought of as stuff is mostly empty space. Atoms themselves are tiny nuclei surrounded by vast regions where electrons buzz in strange probabilistic clouds. Dive deeper, and the nucleus is not a solid lump, but protons and neutrons made up of quarks held together by gluons. At this level, space and time are the silent backdrop where quantum fields ripple and interact. But here's the twist: some physicists, like Carlo Rovelli, suggest that space and time aren't fundamental at all. They may be emergent properties like temperature or pressure. Temperature doesn't exist in one particle, it's a collective effect of many particles moving. In the same way, space and time might emerge from something more basic, possibly a web of quantum information. If that's true, asking what is space is like asking what is the ocean, without knowing that it's just an arrangement of molecules. This concept pops up in the holographic principle, proposed by Gerard 't Hooft and further developed by Leonard Susskind. It suggests that everything inside a volume of space can be described by information encoded on its boundary, much like a 3D hologram is encoded on a 2D surface. Black hole thermodynamics backs this up. The information content of a black hole scales with the area of its event horizon, not the volume inside. This has led some to speculate that the entire universe could be a holographic projection of underlying quantum data. It's a disorienting thought, but let's bring it down to earth for a moment. Consider your daily commute or a walk in the park. You think of it as moving through space as time ticks by. But in Einstein's space-time view, you're always moving through a four-dimensional continuum. If you're sitting still in space, you're moving forward in time at the maximum possible rate. If you're moving quickly through space, you spend some of your motion budget there and move more slowly through time. It's not something you notice at walking speeds, but for astronauts on the International Space Station orbiting at 7.66 kilometers per second, time dilation is measurable. They return to Earth having aged a fraction of a second less than those who stayed on the ground. Even our concept of now gets fuzzy in relativity. There is no universal clock ticking everywhere in sync. Two events that seem simultaneous to you may occur at different times to someone moving relative to you. This isn't just an abstract thought experiment, it's something GPS satellites must account for. Their onboard clocks run faster due to weaker gravity at their altitude, but also slower due to their motion. Engineers carefully adjust for both effects so your phone can tell you where you are. On a cosmic scale, time takes on another role. It's tied to the expansion of the universe. The further away a galaxy is, the faster it's receding, Not because it's flying through space, but because space itself is stretching. This is why distant galaxies appear redshifted there. Light's wavelength is stretched along with space. In effect, looking farther into space is also looking back in time, because light takes billions of years to reach us. Here's where it gets personal. Every time you look at the night sky, you're seeing not the universe as it is, but a time-laced tapestry. Each point of light, a story from a different chapter of cosmic history. You might be looking at a star that no longer exists. Its light still traveling toward you across the gulf of space-time. It's fact that every glimpse upward is also a glimpse backward has a way of humbling the mind. And yet, despite all our theories, space and time still resist complete understanding. Are they truly continuous, or are they made of indivisible quanta? Is time an arrow that inevitably moves forward, or is that just an illusion born from entropy? Some researchers, like Sean Carroll, argue that the arrow of time is tied to the universe's lorentropy beginnings. Others suspect time might emerge from timeless laws when viewed from within the system, meaning that, from a God's eye view, all moments might coexist. At the tiniest scales imaginable, our smooth picture of space-time begins to break down. This is the realm where quantum mechanics and general relativity clash, and where quantum gravity theories like loop quantum gravity and string theory attempt to reconcile them. If you could somehow zoom into that level, space might not appear as a continuous fabric, but as a frothing, ever-changing quantum foam. In this foam, tiny wormholes may flicker into and out of existence, and the concepts of before and after could become meaningless. Physicist John Wheeler coined the term quantum foam to describe this wild, fluctuating microstructure. In his vision, space-time itself is alive with quantum uncertainty, constantly reshaping itself. If this is true, then the universe we experience, the stable, predictable version, may just be an average picture smoothed out over incomprehensibly small distances and times. The reality beneath could be far more dynamic and strange. String theory offers a different take. It replaces point-like particles with one-dimensional strings whose vibrations give rise to all particles and forces. In this framework, space and time might emerge from the interactions of these strings and the underlying geometry of extra dimensions curled up at tiny scales. Some versions of string theory even suggest that our universe is like a 3D brain floating in a higher dimensional space. If so, what we call space could be just a slice of a much bigger reality. In loop quantum gravity, proposed by physicists like Carlo Rovelli and Lee Smolin, space-time itself is made up of discrete chunks like atoms of space. Instead of a smooth continuum, reality is woven from finite loops connected in a network called a spin network. Time doesn't flow in this picture, it emerges from changes in relationships between these loops. The familiar ticking of seconds is a large-scale effect of countless tiny transitions. But here's where it gets fun for the imagination. If space and time are emergent, then it's possible they didn't exist in the earliest moments of the universe. Before the Big Bang, or rather, before space-time as we know it, there might have been something timeless, a primordial state governed by pure quantum rules. When space-time condensed out of this state, the arrow of time as we experience it began. From our perspective, this is the birth of the universe. From the perspective of the timeless state, there was no before to speak of. Daily life gives us analogies for these mind-bending ideas. Imagine heating water on a stove. At a certain point, bubbles begin to form, and a new phase emerges: boiling water. Before that, there was no boiling to talk about. In the same way, time and space may have boiled into being out of some deeper, structureless reality. We live in the bubbles, never seeing the stillness that came before. And yet, we constantly navigate space and time as though they're absolute. You wake up, check the clock, head to work, meet friends at a cafe. You trust that a meter is a meter, and that 5 minutes for you is the same as 5 minutes for someone else nearby. For everyday life, that's a fine approximation. But venture to the extremes near a black hole or at the speed of light, and those assumptions fail spectacularly. Near a black hole, space curves so intensely that time for you slows down compared to an observer far away. If you hovered just outside the event horizon, you could watch the outside universe speed up millions of years. Might pass for them while only hours tick by for you. For the people outside, they'd see you approach the horizon more and more slowly, never quite crossing it in their time frame. Space and time stretch and twist in ways that defy intuition. This isn't just science fiction. Astronomers have observed time dilation effects around massive objects, and experiments like the Pound-Rebka experiment have confirmed gravitational time dilation even on Earth over just tens of meters. Atomic clocks placed at different altitudes tick at different rates, teeny differences, but measurable. So what are space and time really? The more we investigate, the more they resemble tools of description rather than fundamental ingredients. They may be the scaffolding our minds build to make sense of underlying relationships between events, between bits of information, between causes and effects. In that sense, space and time could be like the coordinate grid on a map, useful for navigation, but not real in the way the mountains and rivers are. And if they are emergent, then their future is not guaranteed. Just as they could have appeared from a timeless quantum state, they could one day dissolve back into it. The distant fate of the universe, whether it ends in a big freeze, big rip, or something else, may also be the end of space and time as we know them. In their place, perhaps something stranger and simpler will remain. Think about the last time you were completely absorbed in something. Maybe you were watching a sunset, reading a novel, or laughing with friends, and suddenly, hours had passed without you noticing. That sensation is your brain bending its own version of time. Physics tells us that time can stretch or shrink in the cosmos depending on gravity and motion, but our minds do something similar every single day on a personal scale. The opposite happens when you're restuck in a slow queue or enduring a boring meeting. Minutes feel like hours. That's because our perception of time is tied to novelty. When your brain processes new, rich experiences, it uses more mental markers, making a stretch of time feel full and short. When experiences are repetitive, your brain records fewer markers and time seems to drag. In a way, your personal space-time is being warped by your own consciousness. This personal distortion links back to a strange truth in physics. Time is not absolute. If two people live different experiences or exist in different environments, their clocks, whether physical or mental, can disagree about the passage of time. On Earth, the differences are too tiny to feel physically, but mentally, they can be enormous. Your mind is its own time machine, shaping reality according to emotion and memory. Now, space plays a similar trick on us. When we imagine space, we think of distances measured in kilometers or miles. But your brain's map is emotional and psychological. A room you love feels warm and close. A dreaded destination can feel far, even if it's just down the street. In that way, we carry our own mental geometry that overlays physical space. And this is where it gets fascinating. Physicists like Carlo Rovelli suggest that reality itself may be relational. That means space and time aren't giant universal backgrounds, but webs of relationships between events, objects, and observers. Just as your friend's version of yesterday or far away might differ from yours, the universe's version depends on where and how you look. Here's a relatable analogy. Imagine life as a huge, sprawling party. Space is like the layout of the rooms and hallways, and time is like the music playing. For each person, the music might be louder or softer, faster or slower, depending on where they stand. Two people can be in the same house, but having completely different experiences. This is how space and time can exist differently for different observers. And yet, for all this weirdness, we still cling to the illusion that they're fixed. We schedule our days and hours, mark our years with birthdays, and draw neat maps of continents. But just as maps are not the actual terrain, our measurements of space and time are not reality itself. They're conveniences, tools, a way of navigating a much stranger landscape. If you think about it, This has a liberating twist. If time is flexible and space is a network of relationships, then the way you live your moments matters more than the objective ticking of a clock. The most expansive spaces might be inside your own imagination. The longest journeys might happen in a few intense seconds. In a cosmic sense, your perception is part of the architecture of the universe. Imagine you're sitting in a cafe, sipping your drink, watching people go by. You might think the future hasn't happened yet. The past is behind you, and you're stuck in the present moment like a bead on a string. But some physicists would argue that's not how the universe actually works. Einstein's theory of relativity hints at what's called the block universe view. In this picture, the past, present, and future all exist at once, like different frames in a film reel. We only experience them one frame at a time because our consciousness moves along the reel in a single direction forward. But the whole reel is already there. This raises mind-bending possibilities. Maybe the future already exists, and maybe time isn't something that flows at all, it's just our perception moving through a fixed landscape. Think about a book on a shelf. All the chapters exist simultaneously, but you experience them in a sequence, page by page. From your perspective, the future chapters are not yet, but in reality, they're already written. The universe might be like that. If that's the case, then every place you've been and every moment you've lived is still out there, somewhere in space-time. You could, in theory, travel to them if you could move in time like you move in space. The tragedy and beauty is that we can't act, least not yet. But knowing they exist might change how you see your memories. Instead of being gone, maybe they're simply elsewhere in the cosmic library. Now About Space isn't just a stage for events. According to general relativity, space is shaped by matter and energy. A star bends the space around it, like a bowling ball bending a trampoline. Light itself follows these curves. And here's where it gets even stranger. Space might not be a thing at all, but a pattern of relationships. Physicist Lee Smolin suggests that space emerges from a web of connections, not as an independent entity. That means space is more like a living, shifting network, always influenced by what's in it. It's not the rigid, empty container we imagine. It's dynamic, alive in a way. Bring it back to your own life for a second. Imagine your relationships with people as this kind of space. Some people are closer to you not because of physical distance, but because of the emotional connections, like space bending around massive stars. Your relationships bend the mental map you carry in your head. Space and time aren't just coordinates in a physics textbook. They're part of the way the universe organizes reality. But that organization is far more flexible, strange, and intimate than our daily experience makes it seem. The more you think about it, the more you realize we're not moving through space and time. We are space and time. So, if space and time are not fixed, unchanging backdrops but flexible, living parts of the universe that opens doors to ideas that seem like pure science fiction, but they're not entirely impossible according to modern physics. One of these is the concept of wormholes. Imagine space-time as a sheet of paper. If you draw two dots far apart, you can trace a long line between them. That's the normal path. But what if you fold the paper so the dots touch? Suddenly, the distance between them disappears. That's the idea of a wormhole, bending space-time so that two distant points are connected directly. Now, most of the time when scientists talk about wormholes, they describe them as highly unstable, needing exotic matter to hold them open. But even that word, exotic matter, sounds like a mystery waiting to be solved. It's the kind of stuff that could have negative energy density, something we've never actually found, but which isn't forbidden by the laws of physics. If we ever manage to create or discover it, we might build shortcuts through space and maybe even time. Speaking of time, let's explore one of the strangest implications of relativity: time dilation. You experience this every day, even if you don't notice it. Your head is ever so slightly farther from the center of Earth's gravity than your feet. So technically, time is moving a tiny bit faster for your head than your feet. The difference is unimaginably small, but it's measurable with atomic clocks. And the higher you go, the faster time moves. Astronauts on the International Space Station age a little bit slower than we do on Earth, because they're moving fast but also a bit further from Earth's gravity. Now, here's where it gets deeply personal. If you've ever felt that time flies when you're happy or drags when you're sad, you've already experienced a form of time dilation just in the theater of the mind. Physics tells us that our emotional state doesn't physically change time, but it absolutely changes our perception of it. So in a way, you are your own time machine, stretching and compressing the flow of moments in your experience. And then there's the idea that maybe the universe itself is timeless. Some interpretations of quantum gravity suggest that time might not be a fundamental part of reality at all. It might be something that emerges from deeper, timeless laws. Imagine if the clock of the universe is just a construct our consciousness needs to make sense of events. Like a movie projector giving us the illusion of motion from still frames. In your daily life, think about photographs. Each picture is a frozen moment. Flip through them quickly and you see movement. But the movement isn't real, it's an illusion created by your mind linking those still frames together. Some physicists think our reality might be like that, with now being just one still frame in a cosmic photo album. If this is true, then asking what is space and time, really, isn't about measuring distances or seconds. It's about understanding our place in this strange, possibly eternal structure where all moments may already exist. And that's where it gets both thrilling and humbling. We might not be moving through time at all. Time might be moving through us. Think about this. Carlo Rovelli, one of the most well-known modern physicists, describes time as not a universal flow, but something deeply local. In his view, every place in the universe has its own clock, ticking at its own rate depending on its speed and gravity. That means your now might not match someone else's now, in another part of the universe. And if you stretch this idea far enough, it almost sounds like there's no single, shared present moment at all. Kip Thorne is famous for his work on gravitational waves and for being the scientific brain behind Interstellar. Pushes this idea further when talking about extreme gravity. Near a black hole, time slows so dramatically that an hour for you could be years for someone far away. This isn't science fiction. It's built into the fabric of Einstein's equations. Thorne even explained that if you could hover close enough to a black hole without being ripped apart, you could essentially time travel into the future, because when you came back, the outside universe would have aged much more than you had. Sean Carroll, another theoretical physicist, often speaks about the arrow of time, which is our sense of time moving from past to future. He links it to entropy, the measure of disorder in the universe. In the simplest terms, things tend to go from neat to messy, not the other way around, and that's why we experience time as moving forward. A dropped glass shatters, but it never reassembles itself. A banana rots, but it never unrolls. And our memories are always of the past, never the future. Now, bring this back to your everyday life. If you've ever looked at an old photograph and felt a wave of nostalgia, that's your brain traveling in time, at least internally. You're not just remembering facts, you're reliving sensations, emotions, even smells. That experience hints that, in a way, the past is still there, like a saved file on a cosmic hard drive, even if you can't directly walk back into it. Here's a mind bender. There are theories suggesting that past, present, and future all exist simultaneously. And it's only our consciousness moving along this timeline that creates the illusion of flow. Imagine a movie reel where all the frames already exist, but the projector, your awareness, lights them up one by one. That would mean your future is already out there, waiting for you to arrive. And the more you think about it, the more it feels like space and time aren't just physical structures. They're part of the stage on which our minds perform. That stage could be curved, twisted, and looped in ways we can't yet imagine.